All right, guys, I want to start talking about 8.3, which is going to be, it's called in your textbook trigonometry, but we've been doing trigonometry, but this is kind of one of the key components to really progressing through the rest of trigonometry. So the things we've done with like Pythagorean theorem, like so trigonometry, the word there, tri meaning three, gon meaning angle, metry meaning measurement. So we're talking about put all that stuff together, triangle measurements, right? We've been doing that. We've been doing that since essentially chapter 4. So it's in order, I guess, to progress further with understanding and analyzing triangles is to start introducing what we call trigonometric ratios, okay? And we're going to need our calculators to do this. So either get your get a TI-83 out, get one of those red calculators that I have, or the little blue ones that you guys might have, just any calculator you've been using, because we're going to have to use them today, because there are, so with the special right triangles, there are ratios that we can recognize through the Pythagorean theorem and exist through the Pythagorean theorem, but there are also other ratios that exist for triangles that maybe right now we're neglecting. So right now we know we got a 30, 60, 90 triangle. We can use the 30, 60, 90 template to find missing values. But if I've got a 20, 70, 90, or a 10, 80, 90, or a 15, 75, 90, how do I address those triangles? Okay, our calculators are going to be programmed to do that, but I want to show you how they're programmed and where the information that they're getting comes from. Because I think if you understand that when I push sine of 30 on my calculator, why it spits back 0.5 every single time. Or when I hit cosine of 30, why it spits back 0.866 every single time. I want you to understand that. If you understand that, maybe you have a better understanding and better grasp of how to apply this information to use it meaningfully. Okay? So the first thing I want to do before we get into anything, I want to kind of look at your calculator and open it up and make sure we're in what we call the correct mode. Okay? On your calculator, there are two things that you can do with angle measurements. And there's two ways we measure angles. One of them is with degrees, and you guys are familiar with degrees, right? Okay? Usually when we're talking about angles, we're anywhere between 0 and 180, but we can do larger. We can go between 0 and 360. We can actually even go further than that. We can go any measurement as high as we want to. If I want a 1,052-degree angle, we can do that. Okay? Working inside trigonometry, and of course inside trigonometry, we'll talk about why that's possible, how that's possible. But we can talk about angle measurements, okay, with degrees. You guys are familiar with that. There's another tool or another unit that we can use, and it's called radians, okay? Now, radians are not all that comfortable for you because you've never been exposed to them. You don't use them very often, okay? You've probably never used them, so they would be unfamiliar to you, so things that are unfamiliar are usually uncomfortable, right? For instance, if I talked about going from here to Cleveland, you would probably talk about that distance in what unit? Miles, because that's what we're comfortable with, right? It's what we use on a regular basis. The more appropriate way, probably the most convenient way to do it, algebraically, is to actually talk about that distance in kilometers, okay? Because then it allows me to quickly convert to other units of measurement if I need to. We're uncomfortable with kilometers, are we not?
No.
Okay. Are we less comfortable with kilometers than we are miles? Yes. Okay. If I ask you, what's 35 kilometers per hour feel like, you're not sure. If I say what's 35 miles per hour feel like, you know what that's like. Okay. So our exposure to kilometers in the metric system is negligible. Therefore, our comfort level is not as good as it is with miles and inches and feet and that sort. Same thing happens with measurements of angles. Okay. For instance, so let's go back to the mile thing. If I'm talking about here to Cleveland, okay, let's say it's X amount of miles. Well, if I change that into X amount of kilometers, those two numbers would be completely different, right? But are the distances still the same?
Yeah.
Yes, the amount that I travel is still the same. So when I'm talking about radians and degrees, a 30-degree angle corresponds to what we call a pi over 6 radians. It's still the same exact angle. It's the same exact size. It's just two different ways of identifying it and talking about its size. Does that make sense? Okay. Different units. What you're more comfortable with is degrees. But what is more natural and what is more algebraically intelligent or useful is to talk about angle measurements in radians. So we'll get to that point eventually. But the reason I bring that up is because your calculator is probably set in one of those two modes, okay? And if I'm going to be doing all the work with degrees in my question and my calculator is set in radians, it's going to be wrong. It'd be like my calculator, for some reason, if I was able to do this, do all the work to find out how many miles it was, but my calculator was stuck in kilometers. It would be wrong, right? Does that make sense? So we have to make sure that our tool that we're about to use is set up correctly, okay? Maybe some of you worked with your parents on fixing cars or something at the house or whatever. My father was a mechanic, and he always asked me, hey, go get the channel locks or crescent wrench or whatever. I knew what tools to get, but when he asked me to use them to help him out, I usually used them wrong, and I didn't get the job done efficiently. He would take the tool from it, and he would do it in an instant because he knew how those tools worked to his benefit, right? It's the same thing with your calculator, okay? You're not going to get to an efficient answer if you don't know how it works. So what I need you guys to do, I need you, if you got TI-83 or 84, okay, I need you to hit the mode button. Those of you that don't have this calculator, just hold out. But, you know, let's say that Johnny's got this TI-30 right now. He comes to class tomorrow. He left his book bag at home. We got a quiz tomorrow. He's like, hey, can I borrow one of your calculators? And all I got is TI-83 or 84. He's got to know how that works, right? I'm going to teach him the day of the test on how that works. So expose yourself to how different things work, okay? So on the TI-83 or 84, you're going to hit mode. You're going to go down to about the third line where it says radian and degree. You're going to go highlight degree and make sure it's highlighted, hit enter, and then go second quit. And now you've put your calculator in degree mode. Okay, that's what we want. If you have, Johnny, can I see your calculator? A calculator like Johnny's that says TI-30XA or something like TI-30XII or something like that, like my red ones, or any of those versions of calculators where you only got like 2 lines of a view screen or 1 line of a view screen, there should be a DRG button somewhere. It should be close to your second key. If you hit DRG on some of those, it will come up with 3 words, DEG, RAD, or GRD. You want to make sure that DEG is underlined. Okay, so you can move your cursor back and forth to do that, and then hit enter so that DEG shows up. That calculator is nice because if you've done it correctly down the bottom right-hand side or corner of your view screen, it should say DEG. Okay, and a little small typeset. If you've got another one, that if you hit second key, or sorry, if you hit your DRG button, but no words showed up, if you keep hitting it, you should be able to see the tiny words above your number should say 0, and above that number should say like DEG, GRD, RAD, and it should be able to bounce back and forth between that. Is that correct? Okay. You just want to hit that button enough to where it says DEG. All right. We have to be in degree mode for our calculator to work and produce the values that we're interested in here. That being said, when you grab a calculator, one of mine, classroom calculator or friends or whatever, you don't know what the last person that used that calculator did with it. So you need to go check the mode to make sure what you're about to do with it is done correctly. Does that make sense? My trig students usually use radians. Okay? So if you're using my TI-83s, 84s, they happen to be first and second period. If you grab a calculator that hasn't been used all day except for second period, it's in radians. If you just start plugging away and doing your work, you're going to get every single answer wrong because you're in the wrong mode. Okay? You might go through the algebra right, but using your calculator incorrectly poses a problem. If you're in Desmos, one second. If you're in Desmos, okay, because this is an option, and this is the calculator that your end of course exam will give you, okay, it is defaulted to go into radians. Radians is, like I said, it's the most convenient, algebraically, it's the most convenient mode to use, or unit measurement to use. We need to make sure that degrees is down here highlighted. We click on the wrench, just click on that, okay, we can flop back and forth. What's kind of stinks about Desmos is that every time I reload it, so if I shut that website down or whatever and open back up, what does it jump back to? Radians. So I got to change it. Okay. Now that is the calculus presented on the end of course exam to you if you choose to use it. On the end of course exam, when I go from question 1 to question 2, everything regenerates. So in question 1, if I change to degrees, when I go to question 2 and open the calculator up, it's going to regenerate and it's probably going to set it back to radians. Does that make sense? Okay. You have to be cautious of that. The first year that end of course exam was taken, A lot of people miss questions because they didn't realize that the calculator was resetting itself back to radians every single new question, okay, that dealt with these trigonometric ratios. So we need to be able to do that, all right? GeoGebra, a little bit different. I'm going to show you how to use GeoGebra right now. GeoGebra is actually predicated off of degrees first. So it should be all right if you open up GeoGebra and start using it right away. What I want you guys to do to make sure everybody's got the right mode, type in sine of 30. Sine of 30. What did you get back? 0.5. 0.5. Everybody got that? So what that means then is that every single time that I deal with a triangle that has a 30-degree angle, if I type in sine of that 30, it's always going to give me back 1/2. If I want to talk about why it gives me 1/2 and what that number is actually representing. What is that? It's 0.5. It's always going to give it to you as decimal, but it's a ratio. It's 1/2. I want to talk about where that comes from. Okay? So it's going to be a little bit of a process from what we've already done with similar triangles in Chapter 7. So let me close some stuff off here. Okay, so I've got a triangle here. You guys agree I got two triangles there, red one, blue one? Okay, would you agree that they both have that angle of 30 degrees in them? Okay, so they both got angle B in them. They both also have angle E and angle F that are right angles. So those two triangles, red one, blue one, are what to one another? They're similar. Okay, so I want to go through a little bit of a similarity practice that we've done quite a bit of in the last couple of weeks. I want to take give me a second here and get this thing turned on. All right. All right, I want to take triangle. I'm going to name the red one as triangle ABE. And we'll say it's similar to triangle CBF. Okay, we've done that before, right? Then from that, we gain that AB should compare to CB. BE compares to BF, and AE compares to CF. Okay? Each one of those, I'm going to write this kind of ratio here. Each one of those is a red value or a distance that came from the red triangle divided by a distance that came from the blue triangle, right? And each one of those, what those ratios ended up becoming was the same every single time, right? No matter if those two triangles are similar, AB divided by CB ended up being the same thing as BE divided by BF once they reduced. And that reduction, that value that became reduced, that ratio became what we call a scale factor, right? And that was the scale factor that says, okay, if it's like a 1 to 2 scale factor, it means that I can use either 1/2 to multiply a distance in the blue triangle to generate a distance in the red triangle, correct? Or to multiply a distance in the red triangle by 2 to get a distance, a corresponding distance in the blue triangle. Does that make sense, everybody? So it's a scale factor that allows you to go from red triangle to blue triangle or blue triangle to red triangle. What we're going to do right now, a little bit of algebra, is manipulate those ratios so that when I have a value out of the red triangle, I can use that scale factor to actually find me another value in the red triangle. Okay? Does that make sense? So I don't want to go from red to blue. I want to go from red triangle to red triangle. Okay? And we should be able to do that. So let's kind of mess around with some proportions here. I could pick out any two of these here, but I want to pick out, I want to talk about the hypotenuses. So CB and AB, so I'll choose that one. And then let's talk about these sides here, AE and CF. So I'm going to kind of quickly write those two things here as AB over CB is equal to AE over CF. Okay? Now, I want to rename those. I don't like dealing with the letters. Let's just kind of get kind of generic here. with the labeling here. So instead of calling it AB, let's call AB, if I look at the part of the triangle that AB is, it's the hypotenuse of the red triangle, right? So let's just say hypotenuse, and I'll put red in parentheses here. So AB would be the hypotenuse of the red triangle. What is CB? If I'm going along the kind of same lines of logic there, what would you call CB? Using the same logic that I renamed AB, hypotenuse of red, you'd call CB the hypotenuse of the blue. Okay. Now AE being this distance here, all of this stuff is going to, the reason I'm doing this, I'm interested in that 30 degrees. Would you guys agree that AE is opposite the 30 degrees? Yep. Okay, so I'm going to call AE opposite for the red triangle. And now with the length that it's actually opposite the 30 degree angle in the red triangle. You could do that too, yeah. But I want, because I don't really care that it's the smallest side. I care that it's opposite that angle. Would you agree that CF is opposite that angle in the blue triangle? Okay. So that's exactly what we have said since chapter 7. Okay. But I want to do a little bit of an algebra game here to see that what I'm about to do, what we're about to do, is possible. If I take 2/3 equal to 4/6, would you guys agree that's a true proportion? Mm-hmm. Have we talked about the ability of taking those two things and replacing them and still getting something that is true? Okay, we've talked about being able to do that, right? Now, 2/3 and 4/6, that ratio is like 0.66666 repeating, right? 2/4 and 3/6 are both 1/2 terminating, but they're both true. The top one, 0.6 repeating, equals 0.6 repeating. That's true. 0.5 equaling 0.5 is still true, right? So we're allowed to flip-flop those two things. So let's come down to, because we're allowed to do it there, that must mean we can do it everywhere, right? I think we talked about just kind of generically, if I had like A over B equals C over D, if I cross multiply, I get BC equals AD, right? Well, if I flip-flop those and rewrite it as AC equals B over D, when I cross multiply, do I still get BC when I cross multiply those two? Do I still get AD when I cross multiply those two? So that's kind of a proof showing you that I can do that regardless of my numbers. It doesn't have to be 2/3 and 4/6. It can be anything. I can interchange the means and still get something that's true. So let's come down to this down here, to bottom left down here. We should be able to take that blue one and that red one and interchange them. Now, what did that effectively do? Now, in each ratio, I'm comparing a red distance to a red distance, right? You see I'm staying inside that red triangle in that ratio? Previously, I had a red distance compared to a blue distance inside that ratio. And that was essentially a scale factor that allowed you to go from one triangle to the second triangle. Now I've got a scale factor that allows me to stay within one triangle. Okay? Now, it's not really necessary, or I guess not 100% finished here. I don't want to leave it this way. Here's my next question to you. Is this true? If I say 2/3 equals 4/6, can I rewrite this as 3/2 equals 6/4? If I cross multiply, do I still get a true proportion here in blue? What did I do from that one to get that one? Okay, that one to that one? Okay, so I'm flipping it as giving the reciprocal, right? So can I do this? Flip that one, as long as I flip this one? Okay, so now, the reason I do that is because now when I take, with GeoGebra, take these distances. So opposite, so I'm always referencing the 30-degree angle. Opposite in the red would be AE, right? AE. I'm going to divide that by the hypotenuse of the red. Hypotenuse of the red is AB. It's going to pull out those two distances. So those two distances, AE is 2 and BE, or not BE, sorry, AB is 4. See how it pulls those two distances out and divides them? Gave me 1/2. Okay? If I do the opposite of blue, so that's CF, and divide it by CB, what's it going to give me? 0.5. It's because it takes this distance here, do it this way, that distance there, divides it by that distance there. Now let me change the rounding here so we can fit it all in here. So 3 decimal places. Takes those two numbers and divides them. And it gives me, over here you see, 1/2, right? The argument then is, well, is that true for every single triangle that has a 30-degree angle in it? Well, as I move this, do you see how that blue triangle changes? Do you see how CB and CF change, right? Okay, so as let me just kind of clean things, let me erase all this stuff. As I move, you see on the left-hand side, distance CB, distance CF, those are respectively changing, right? This is the quotient of those two things. Does that ever change? No. So it's telling me that no matter what right triangle I have, as long as it has a 30-degree angle in it, the opposite side divided by the hypotenuse is always going to reduce to 1/2. Does that make sense? What is nice about that? Well, if I know that that is, let's just look at the blue one now. If I know that hypotenuse is 9.72, can I use that 1/2 ratio to multiply this by 0.5 to get that distance? Does that make sense? Or if I know that distance, can I use the ratio of 2, which would be the reciprocal of 1/2, to generate my hypotenuse? Okay. So that's awesome. That's really nice. Now, the reason I dealt with this in a 30, 60, 90 triangle first is because that 1/2 should make sense for another reason. If I'm working inside a 30, 60, 90 triangle, isn't this side here in across from 30? Isn't that side 2 in? When you compare the opposite side to the hypotenuse, what happens with your ends? Cancel out. Okay? So there that 1/2 generates again, maybe using a different approach, using the special right triangle approach. Okay? But here's where things get kind of interesting or useful in regards to this process. Because every triangle that I deal with is not a 30, 60, 90. It's not a 45, 45, 90, right? In general practice, most of my triangles are not those things. So what do I do? Have a triangle that has a 38.8 degree angle in it. Well, if I take the opposite divided by the hypotenuse of a triangle that has a 38.8 degree angle in it, a ratio of 0.627. Okay? Does that make sense? Now, how do I get that ratio? My calculator is stored with that ratio. Opposite divided by hypotenuse we refer to as the sine function. Okay? So type in on your calculator real quick, hit the sine key, and that's why you got to be in degrees. You hit the sine key, and now type in 38.8. And you should get something close to 0.627. Okay? Now, mine's rounded to the 3 decimal places. Yours goes out to 10. Okay? Does that make sense? Okay, so that is giving me then the ratio that going to do this real quick. If I were to take, I'm going to hide this number for you. Whoa. Take, okay, take that number right there, 7.861, 7.861. Type that in your calculator. Okay, so the ratio that I had, so what we had, 38.8, is that what we had? Let me get that back up here. Okay, take that number of 7.861 and multiply it by 0.627. 0.627 gives you 4.92. Okay, what is that 4.92? It is, no, It is that side length. Does that make sense to everybody?
Yeah.
So the .627 number, or sine of 38.8, is the stored ratio that allows me to go from one side of my triangle to the other side of the same triangle. Does that make sense? So what this allows us to do, if I know an angle and I know a side length, it's a scale factor that will generate the other side lengths. Okay? It is also something that will eventually, if I know two side lengths, actually an angle. Okay? But what we just talked about is kind of the proof of why the sine, which we call SINE, is equal to opposite leg divided by the hypotenuse. This only works for right triangles right now. Okay? So sine is equal to opposite leg divided by hypotenuse. Now, the thing that we do is, because the opposite leg changes per angle that I'm looking at. So right now I was looking at angle B, right?
Yeah.
Well, I could do the same thing with angle A or angle C in those other triangles, or the other acute angles. If I'm looking at angle A, there's a different side that is opposite A than the side that is opposite B. Does that make sense to everybody? So when we're dealing with sine, cosine, and tangent, the first thing we have to do in order to get things kind of situated correctly is that we have to identify the angle that we're interested in. And usually it's the angle that's been provided for us. Either the angle they're asking us to find the measurement of, or the angle that they give us the measurement of. Okay, that's going to kind of draw our focus there. So here, maybe they tell me angle A was the 30-degree angle or something like that. Okay? I like to draw my little arc in A, and I think about it as kind of being an eyeball. If that's an eyeball, my eyeball is always looking at the opposite side. Does that make sense? Okay? I label that the opposite side. I've been doing this, guys, since I was in your seat, in this exact same classroom. And I still relabel all my triangle sides because it's the safest thing to do, and it takes about 3 seconds to do. Okay? So much better to waste 3 seconds and be right than it is to save those 3 seconds and be completely wrong, right? So I'm going to label that as opposite. I'm then going to find my right angle and go opposite it and write down my hypotenuse. Okay? And that leaves one side left over that doesn't have anything written in it, and we call that the adjacent side. So this would be the leftover side here, we call it adjacent. Now there is a question, well, isn't the hypotenuse adjacent? Would you guys, adjacent means next to, right? Okay, so would you guys agree that AB is next to that yellow angle A? Yeah, okay. Would you also agree that the hypotenuse is next to it? But you never call your hypotenuse adjacent. Does that make sense? Being the hypotenuse is kind of prestigious for the triangle, right? To be the biggest thing. So hypotenuse takes precedence over being adjacent. So it's always labeled hypotenuse. Okay? If you can label opposite hypotenuse first, then you'll never be wrong labeling where the adjacent side goes. You see with the exact same triangle, if I focus over here on angle C, does it produce a different opposite side? A different adjacent side? It's the same hypotenuse though. Okay? So in the last slide we said sine. If I were to say sine of A, always put the angle there for us. So let me write that a little bit better. It looks like this. We say SIN. We still read it as sine. Okay? We put the angle in those parentheses. And then it's opposite over hypotenuse. If I was to label this, opposite would be BC. Hypotenuse would be AC, right? Over here, if I look at sine of angle C, opposite it is AB. Hypotenuse is AC. Do you see how those ratios would be different? They're different, and it's important that we understand they're different because we're focused on different angles initially, and that then sets up different opposite and hypotenuse sides. Okay? Does that make sense to everybody?
Yep.
All right. When we deal with trigonometric ratios, you see 3 of them on your calculator. We worked through that GeoGebra showing just how the sine evaluated and gave us kind of that 1/2 or what are those other ratios that we were coming up with when we had like 38.8 degrees and all that kind of stuff. There are 3 trigonometric ratios. There's actually 6. But we're going to talk about 3 of them right now in great detail, and then we'll talk about the other 3 later. But if I'm looking at this triangle, using this triangle, capital A up top being the angle I'm interested in, opposite side, adjacent side, hypotenuse correctly identified. Sine is opposite divided by hypotenuse. Opposite divided by hypotenuse. Okay? Cosine is always adjacent divided by hypotenuse. And tangent is always opposite divided by adjacent. Okay? My thought is, guys, that you could probably do this stuff without any of that introduction of similar triangles that we talked about with GeoGebra at the beginning. But my thought is also that if you understand what we did there with similar triangles, it makes using this stuff a little bit easier, and it makes, I think some people, they do things in math but aren't really sure and comfortable why it's working. I think if you understand why it's working, you develop a better comfort level with it, right? Okay, and if you get stuck because you know how it works or why it works, maybe you get yourself unstuck because of that. Okay, so that's why I like to introduce that kind of stuff. But I can show you the steps. You can all do this by me showing you the steps. I want you to understand. I just don't want you to be a robot doing something, right? Okay, I want you to have some meaning and understanding behind it. So every time I talk about sine, cosine, and tangent, those are the ratios that I'm looking at. Okay, now there's a mnemonic device that allows us to remember this a little bit better. You guys, a mnemonic device, you guys know what that is, right? Yeah. Okay, so like King Henry died by drinking chocolate milk, right? It's a phrase that allows me to remember something academic. So SOHCAHTOA is the phrase that allows me to remember this. Okay? Now, so they're three-letter acronyms. The first letter in each one of those acronyms stands for either sine, cosine, or tangent. Okay? The last two letters tell you how you divide the sides that relate sine, cosine, and tangent. So SOHCAH, S-O-H, sine is the S, O is opposite, H is hypotenuse, right? And it's left to right, we would divide them the way we see them. So O divided by H. Cosine is A divided by H. Tangent is O divided by A. Is it okay with everybody? Yep. Okay. So SOHCAH, you've heard that before, right? Yeah. Okay. So Ms. Cole taught this a little bit last year?
Can I get told that?
No. All right. So last year you learned how to use it. Did you learn why it was that way? No. Okay. I think so. So there's a couple things that we like to do with SOHCAHTOA. There's a couple different types of questions that show up. The first one is a question like this, where it says, here are three side lengths of a right triangle. Can you write what the trigonometric ratios are for a particular angle? So they give me angle T here. I want to find sine of T, cosine of T, and tangent of T. This is the process that you go through for this question. I'm going to identify T. That's the angle that I'm interested in, right? Okay, I draw a little arc. It reminds me of an eyeball. 8 would be what side? Opposite. 17 is?
Hypotenuse.
Hypotenuse. I like the conviction. And 15 is? The adjacent. Okay? So when I write, so they ask me to find the sine, cosine, and tangent. I write sine, and then in the parentheses, we write capital T. We label the angle that we're interested in. Sometimes it'll be a letter, like it is here. Other times, if I know it's 30 degrees or 52 degrees, something like that, I'll put the degree in there. But that's representing an angle, what goes in there. We call it the argument. Okay? Every time that we're in a math class and we're dealing with something that's usually non-polynomial, a lot of times they bring in words like logarithms or the sine, cosine, tangent. We have parentheses, a word, and then parentheses. That thing in the parentheses is usually called an argument. Okay? For sine, cosine, tangent, the argument is always an angle. Sine is opposite over hypotenuse, right? What's the opposite side here? 8. What's the hypotenuse? 17. Okay? So what does this mean to me? What does that 8 or 17 mean to me? It tells me that every single triangle, every single right triangle that has that angle T in it, now I don't know how big angle T is, but let's say I had another triangle. Let's say I had this red triangle sitting on top. Would you agree that that red triangle has T in it? Angle T? That means that whatever that side is and whatever that side is, when I divide them, what are they going to divide down to? 8 over 17. Does that make sense? Okay? No matter what right triangle I have, it's got angle T in it, it's always going to divide down to 8 over 17. Now, traditionally speaking or normally speaking, we're going to have that number. We'll know what t's measurement is. Okay? Can I find cosine? Yeah. Cosine we said was adjacent divided by hypotenuse, right? So it would be 15 over 17. And then tangent of t, what did we say tangent was? Opposite over adjacent, right? Something, I didn't talk about this with the other class, but this is an interesting feature, and it's one that we use quite a bit later on. Does anybody know what I can do with those two numbers to get that one? If I take 8 over 17, divide it by 15 over 17. Do you guys remember how to divide a fraction by fraction? Okay, the 17 is doing up, cross out in this case. But if they were different, we would take the bottom fraction, multiply by its reciprocal. Does that give me, do the 17s cancel then? Give me 8 over 15, which is that number right there. What was 8 17ths the same as? 8 17ths we said was sine, wasn't it? 15 17ths we said was cosine. So what we find out is that tangent of t is actually whatever sine of t is divided by cosine of t. So that's a neat relationship that's useful for trigonometry. Okay, and we'll talk about that later on and do more work with that. But that is an observation that might be useful. So that's one thing they'll ask you to do. Okay. Something I didn't mention, you know, when I see those sine, cosine, and tangent written that way, S-I-N, we don't read that sin A. We don't read it cos A. We don't read it tan A. Does that make sense? Okay. You know, for some reason, if I'm you know, writing something about, you know, listing things in like English. Let's say Alex has, he's got good hair, he's got clean fingernails, he's smart, okay? He's cute. And then I put comma ETC. How do I read ETC? Etc. You don't come across ETC when you read it and go, right? You don't do that. So when I see sin, which is representing sine, I write or read sine. Does that make sense? When I see COS, I read it as cosine. The reason for sine and cosine, we'll talk about this in a couple days. Sine and cosine, pretty similar words, aren't they?
Yeah, no.
Only thing that changes is that prefix CO, right? Anybody want to know what, or anybody think they know what CO stands for?
The opposite of.
Close. Well, what do you know about angle A and angle C in a right triangle? They're the acute angles of a right triangle, and we had one property about them that was always true. They add up to 90. What's the word? What's the word for two angles that add up to 90? Complementary. What's the first two letters of complementary? CO. CO. Okay. So sine. Listen. Sine and cosine. Okay. They're referred to as cofunctions because the angles that they represent are complementary with one another, and we'll talk about that as we move on in the next couple days. Okay. That's a question that in the past the end of course exam has tried to target to see if you understand. So we'll definitely talk about it. Here's the reason why we want to do these types of or have this understanding of sine, cosine, and tangent, because it allows us now, if I know that I have a 54-degree angle, what we talked about at the beginning of class with those similar triangles, okay, that a 54-degree angle, if I type in sine of 54 on my calculator, it's 0.809 as a decimal. Now it goes on beyond that, but 0.809. What that tells me is that is a scale factor that's going to allow me to take 17 and reduce it down to get W. Does that make sense? Okay. So we're going to go through the process of the algebra that accurately gets me that every single time. Because some people, especially with ratios, we're uncertain. Do I multiply by 0.809 to shrink 17, or do I divide by 0.809 so that I enlarge 17? We're uncertain about that multiplying or dividing. You've all done it with converting things in science or something like that. If I have, miles and I want to go to feet, do I multiply by 12 or divide by 12? Okay. Or sorry, if I want to go from miles, let's go miles to feet. Do I divide by 5,280 or do I multiply by 5,280? We always have that question, right? So it's the same concept here. Do I divide by my ratio, my scale factor, or do I multiply? This should allow us to get it correct every single time. So what we do is we identify the angle that I'm interested in. The angle that I'm interested in is 54 degrees. That's the one they present me, right?
Yep.
All right, then I'm going to label everything off of that. What is this side off of 54? Opposite. What is 17? Hypotenuse. Okay. What would this side here be? Adjacent. I'm not going to label it because I don't have a number there or a value, right? No expression there, so not even going to use that one. Which trig ratio incorporates the objects that I just defined? Okay, so we call it sine though, right? So sine, when I open that parenthesis, what goes in that parenthesis? 54. It's the angle that I defined all my sides off of. And you said it's equal to, sine is, what was the ratio? You said SOH, right?
Yeah.
So opposite would be what?
W.
W. Hypotenuse would be 17, right?
Yep.
This sets up traditionally a proportion for us to cross multiply. If I cross multiply, how many W's you get? 1 W. Cross multiply, I get 17 sine of 54, right? Remember that sine of 54 was that 0.809 number I said that your calculator stored with. So this is going to take 17 times the decimal between 0 and 1, so it's going to shrink 17. Does that make sense? If you type that in, type that number in. Have you made a basket yet? If I type 17 sine of 54 in, I get that number right there, right? That number is the length of W. That's how long that side is, okay? It's the same concept as what we did with 30, 60, 90 triangles. I multiply by 2n or n radical 3 or whatever, but for a 54 degree, or 90, 54, what would the other angle be? 6 or 36? We don't have a template. We have to use this SOHCAHTOA stuff. Yes?
How would you do that on my calculator?
Okay, so on that one, you got to go backwards. You got to hit 54, and then sine. Now hit enter. Okay, so now hit multiply 17. So some calculators, guys, they got to work backwards. And if you have questions on how to work them, let me know. That's why I like to use Desmos or TI-8384. I can just type it in the way I see it, and I get the answer. If I was in the wrong mode, kind of pay attention to this. If I click over to radians, you see that my answer just went to negative 9.499?
Yeah.
That's not a distance, right?
No.
In the way that we think about distance. So I've got to make sure that I'm in the right mode, okay? Or it's going to give me a number that I don't necessarily know whether it's right or wrong, okay? If it gives me a negative number, it won't always be negative when I'm in radians. But I might think I'm doing everything right. Calculator's in the wrong mode. It spits back a number. How do I know if that number is right or not? Okay, I got to make sure I'm in the mode, the correct mode. Is that okay?
Yeah.
Okay. Let's do this real quick because we got time. What would this angle measurement right here be? Right here. 36, right? Okay. If that was 36, what would W be for the 36 degree angle? It'd be adjacent. Okay. So if I did that, can I say cosine of 36 is adjacent divided by hypotenuse? Okay. So can I say 17 cosine of 36? Type that in your calculator. Does that give you the same 13.7 number that 17 sine of 54 gave you?
Yeah.
Think about this. Think about this. Think about this. How does sine of 54 and cosine of 36 relate? Is 54 the same thing as 90 minus 36?
Yeah.
Is 36 the same thing as 90 minus 54? Do you see how that angle right there and that angle right there are what to one another? Complementary. There's where the sine and cosine complementary concept comes into play. Okay? So somebody asked, how do I know which one to use? Doesn't matter. Use the 54. I would use the 54 because it's less work, right?
How would you know you use it?
Okay? Because when I look at 36, W is adjacent to it. It's not opposite it, right?
Yeah.
Okay, so the side at the top, the horizontal side at the top would be opposite 36, correct? Meaning that W would be adjacent. It's the only option for W. So that's cosine is C for cosine, A for adjacent, H for hypotenuse. So K is CAH. So that's how we know that. No new homework tonight, guys, but we're going to come to class tomorrow, and we're going to do as many of these types of problems as we can to get through enough to really get a good grasp of how we apply this stuff. Mm-hmm. Okay, borrow your pen?
It might not be out.
Is that you beeping at me?
You want to do it on